All right, I'm going to do this problem. It's actually not number 32, sorry. This is a special problem. Because I like this problem because it shows you two different ways to do the same problem. We're going to do this problem in two ways. We're going to do it first as energy, and then I'm going to show how you can do it with torque, because now you know how to do both those kind of situations. So what we have is a pulley right here with a mass of 2 kilograms, and we have a weight connected by a rope, two weights connected by a rope, 6.1 kilograms, 2.8 kilograms. And this is 0.7 meters above the ground. So we're going to let this one go because it's more massive. It's going to fall to the ground. But not only is it going to fall to the ground, but it's going to rotate the pulley and it's going to lift this one up at the same time. Up until now, we always treated pulleys as massless because we want to take into account the effect that the mass of the pulley has. But now we have to take that into account. We can't assume that it's massless anymore. And we want to find the velocity right before it hits the ground. So we're going to try to find the velocity of this right before it hits the ground. So we're going to do this as an energy situation. In the energy situation, what's making all of this move is the gravitational potential of this block right here. And this 0.7 actually goes to the center here, but it doesn't matter. It's 0.7 from the bottom until it hits the bottom here. All right, so this is going to be, I'm going to call this one M1 and this block M2. So M1GH is our initial energy. That's the only thing with initial positive energy. The pulley's not moving, nothing's moving, so there's no kinetic energy on this side. Now on the final side, this block is going to go up the same amount that that one went down. So this is going to be M2GH because this is going to go from 0 up. Plus, that's an H, plus this one's going to be moving when it gets to the bottom. So we have 1/2 M1V squared, plus this one will be moving, but it'll be moving up here in this direction. But remember, the direction's consistent. If that's positive, that has to be positive. So this is 1/2 M2V squared, plus the pulley is going to be rotating because we're assuming no slipping of the rope. So this is 1/2 I mass of the I omega squared, where I is equal to 1/2 the mass of the pulley times its radius squared, because we're going to use it as a disk. Alright, so that's it. This energy from this block falling down is going to move this block up. All of these are going to be moving. We want to solve this for V. So to solve this for V, I'm going to move this over here. So I got M1GH minus M2GH is going to be equal to, and notice all these have V in here. I got to expand this one. So this is going to be 1/2 M1V squared plus 1/2 M2V squared plus, and then I, this is going to be 1/2 of the mass of the pulley times R squared, but we're going to place omega squared with V squared over R squared. Those R squareds cancel. Notice there's a V squared in all these terms, so I have to factor that out. I'm going to factor out a GH here just to make this more neater on this side. And this becomes GH times M1 minus M2. Then here I'm going to factor out the V squared. So I'm going to get V squared times 1/2 M1 plus 1/2 M2 plus 1/4, because a half times a half, mass of the pulley. And then to solve for V, I just divide by all that and take the square root. So V is going to be equal to the square root of GH times M1 minus M2 all over 1/2 of M1 plus 1/2 of M2 plus 1/4 the mass of the pulley. Now I have all those numbers, so I can plug all that in. And when I plug all that in, I get that V is equal to 2.14 meters per second. All right, that way is the way most students do it, but that's not the only way you can do this problem. You can also do this problem as torque. So we're going to look at the torque on the pulley. So this is just the pulley. We're going to use the torque method. Now if you look at it, there's a rope going down here, so there's a tension pulling on it this way. And there's a tension pulling on it this way. We're going to call that T2. So T1 and T2. Well, T1 comes from M1's down here. So I'm going to do a free body diagram for M1. And I have M1G here, okay? And I have T1 going this way. And M1G should be longer than T1 because this is accelerating downward. All right, this is moving in a accelerating in a downward direction. All right, and I have to be consistent. So if the pulley spinning counterclockwise is positive, which is what we usually standard do, that means T1 going down, this direction down has to be positive. That looks like a T, but that means positive. So positive is down. And for the other block, for the M2 block, I have M2G, but in this case T2 is bigger than MTG because this block is accelerating upward, and up is my positive direction on that side. All right, so I'm going to use my net torque equation. Net torque just says, here's the radius, that the different forces from the rotation point, which is the center of the block, times the radius times the sine of the angle in between. So the net torque for T1 is trying to make it go in a counterclockwise direction. So this is going to be T1 times R, the distance is away, times the sine of the angle, but the angle is 90 degrees. All right, because it's coming off at a tangent here to the pulley. This one is also at a 90 degree angle. And now T2 is actually trying to make it go clockwise, so that's minus T2 R, sine of 90 degrees. But the 90 degrees just become 1. But it's accelerating, so I replace T net with I alpha. So I alpha is equal to T1R minus T2R. And you look at this and you say, oh look, this is much simpler than this giant equation up here. Well, looks can be deceiving because what we got to replace is what T1, T2, I, and alpha are. So we're going to do all that. So I is still 1/2 mr squared. Alpha is going to be A over R, because remember A is equal to alpha R. So if you solve for alpha, you get alpha is equal to A over R. Okay. And T1. Well, T1 we have to do F net X or Y, you can call it whatever you want. And notice I have positive going down, so this becomes M1G minus T1. And this is accelerating, so M1A is equal to M1G minus T1. I'm going to solve that for T1, or T1 is equal to M1G minus M1A. Okay. I have to do the same thing for T2, F net X, but no positive is going up, so now it's T2 minus M2G. And this becomes M2A is equal to T2 minus M2G. And I'm going to move that over here, and this becomes M2A plus M2G is equal to T2. Okay. Now I have to plug those back in here for T1 and T2. So for T1, I'm going to put in M1G minus M1A, all that times R, minus T2, which is M2A, plus M2G, all that times R. So our simple equation is getting a little more complicated. In this case, we don't have V, we're going to solve it for A, and we know that the acceleration is constant, and then we'll use our constant acceleration equations to figure out how fast it's going. So we can simplify this sum. First of all, that cancels with that, so this is just R here. And then if I divide the whole thing by R, all the R's go away, so we don't even need the radius at all, which makes life easier. So then we have 1/2 times the mass of the pulley on this side, times A, is equal to M1G minus M1A. And then I have to distribute this negative, so minus M2A minus M2G. Now I have to get all the A's on the same side and factor it out. So I'm going to move them all over here. So I'm going to have 1/2 mass of the pulley plus M1A plus M2A. Notice they change signs when you flip them over. It's equal to M1G minus M1 minus M2G. All right. Now I pull the A out. Sorry, there's an A there. Pull the A out, factor that out. This becomes 1/2 the mass of the pulley plus M1 plus M2 is equal to M1G minus M2G. Divide by all that and I get A is equal to M1G minus M2G over 1/2 of MP plus M1 plus M2. Now let's analyze this real quick. Remember, acceleration is equal to force over mass. Newton's second law. Usually you rewrite it as S equals ma, but we can move this down here. Hey, that's what this is. The force making this move is gravity pulling the first block minus the force this one, because gravity is trying to keep this one from moving. So it's the difference between those that's making it move. And the whole mass is moving, meaning both masses are moving. Plus you have to take into account the rotation, which because it's in a disk configuration is 1/2 the mass. So we plug all that in and we find out that the acceleration is equal to 3.277 meters per second squared. And then we want to figure out if we get the same velocity. Well, to do that, we're going to use our constant acceleration equation. Remember this one? We know A now. We know the initial velocity was 0, so we can say V is equal to square root of 2 times 3.277 times our height, but our height in this case was 0.70, and you get the velocity is 2.14 meters per second. Ah, look, you get the exact same answer. So if you have a problem like this, there are two ways to do it. You can do it as energy, or you can do it as torque. With energy, the nice thing about doing it with energy is you don't have to worry about the fact, you just make sure everything's positive, you just have to make sure you get all the energies in there. With the net torque, you got to be really careful about your signs, positive and negative signs, because it's easy to mess up one of the signs and it messes up the whole thing.